All right, so today we are moving on to our next section here, which is explicitly focusing on just arithmetic sequences and series. So by the end of this video, you should be able to find the terms of an arithmetic sequence, find the sum of an arithmetic sequence, and write the equation for an arithmetic sequence and series. So a sequence is arithmetic if the difference between consecutive terms is the same, is a constant. The difference between each number of the arithmetic sequence is called the common difference, and it's denoted by a D. This might sound familiar because you have done arithmetic sequences in Math 1. So let's find the common difference. So in example 1, we have 5, 8, 11, 14, 17. It appears that each number is going up by 3. 5 plus 3 is 8. 8 plus 3 is 11. 11 plus 3 is 14, etc. So our common difference is 3. And notice our last term here, 3n plus 2, that is the explicit formula for this sequence. If I substitute in 1, I get 3 plus 2, which is 5, our first term. If I substitute in 4, I get 3 times 4, which is 12, plus 2, which is 14, which is our fourth term. So we have our explicit formula for this arithmetic sequence, and notice that the coefficient of our variable is also our common difference. Example number 2, 9, 5, 1, -3, -7, etc. It appears that we're going down by 4, so we're adding -4 each time. 9 plus -4, 5, 5 plus -4, 1, etc. And again, looking at that explicit formula, notice our common difference is -4. I have an R here. This should be a D for each one of these. I did not notice that. In our next one, we have 1 and then 7, 6, 4 thirds, 3 halves, 5 thirds. So it appears that we're adding 1/6 each time. Easy way to determine that is to write each fraction with the same denominator. So 6, 6, 7, 6, 8, 6, 9, 6, to see that we're adding 1/6 each time. And again, if you take our explicit formula and you rewrite it in like a slope-intercept type form, we would get 1/6 n plus 5/6, and there we go again, that coefficient of our variable n, 1/6, also matching our common difference. And that's because repeated addition is what multiplication is. Multiplication is repeated addition. 5 times 4 is 5 plus 5 plus 5 plus 5. Or 5 times 4 is 4 plus 4 plus 4 plus 4 plus 4. So that's why we're seeing this repeated addition showing up as a coefficient on a variable. All right, formulas that we have with arithmetic sequences. We have the explicit formula for an arithmetic sequence. A sub n equals a sub x plus d times n minus x. So you can find any term by taking a different term and adding it to d times the difference between the two terms. Or if we want to find a more simplified version of this formula, you could again distribute it out, write it in slope-intercept form. But here's another form as well. It's already simplified, but this is where you get C by doing the first term, take away the common difference. So let's do some examples. Find the explicit formula for the nth term in the arithmetic sequence whose common difference is 5 and whose first term is -1. So here we have our common difference is 5, and the value of our first term is -1. So using the formula above, I'm using the shortcut formula since we know the first term. We have a sub n equals dn plus c. So we have C we get by doing A sub 1 minus D, so negative 1 take away 5. So we end up getting our explicit formula is A sub n equals 5n minus 6. And you could have done this as well with the other formula here. It would have been A sub n equals A sub x, so we'll go with our first term, plus the common difference, which was 5, times n minus x. So since we used our first term, it would be n minus 1. And then when we simplify this, we distribute the 5n and then combine like terms, and we end up getting the same exact formula. So it does not matter which form you use, because when you simplify, it'll be the same. In Math 1, you only used this formula here. You never used this formula here. Okay, the 8th term of an arithmetic sequence is 25, and the 12th term is 41. Write the first 5 terms of the sequence. So let's see here. We know that A sub 8 is 25 and A sub 12 is 41. So using the formula from above, I can say A sub 12 is equal to A sub 8 plus D times 12 minus 8. And again, I'm just using this formula right here. And then substitute in the values we know for A sub 12 and A sub 8. And then this reason is to find D, because we need to find D. So substitute in 41 equals 25 plus 4D. So we end up getting D to be 4. So that means that we add 4 to get the next term, right? That's what our common difference is. It's what we're adding from term to term. So to find the first term, because we want to find the first 5 terms, so I need to find the first, I have, again, using that formula, A sub 1 equals A sub 8 plus 4 times 1 minus 8, which means the value of the first term is negative 3 once we simplify that. So we get negative 3 plus 4 is 1, plus 4 is 5, plus 4 is 9, plus 4 is 13. Example number 6. Find the 10th term of the arithmetic sequence that begins with 8 and 20. So I know that first term's 8, second term's 20. Since I have 2 consecutive terms, it tells me that my common difference is 12, because I had to add 12 from 8 to 20. So using our formula to find the 10th term, value of the 10th term is the value of the first term plus D times 10 minus 1. So we have value of the 10th term is 8 plus 12 times 9, which is 116. I could have also have used the second term here instead of the first term. It would have changed it a little bit. We would have had A sub 10 equals, if we use A sub 2 here, we'd have plus D times 10 would be minus 2, but still would end up giving us 116. Sums with arithmetic sequences. The sum of a finite arithmetic sequence is given by this formula here. Where n is the number of terms, A sub 1 is first term in the series, and A sub n is the last term in the series. So let's do an example. Find the sum of this series. Now, if you're sitting here with a calculator, you're like, why don't I just add all those up? Absolutely. But if you, in this case, it's easy because this is a small finite sum. But what if you had a partial sum of 150 terms, right? That's going to take forever. So we do have a shortcut of an arithmetic sequence. So n is 7, because there are 7 terms here, 1, 2, 3, 4, 5, 6, 7. Value of our first term is 40, value of our last term is 22. So we substitute into our formula. The sum of the first 7 terms is equal to 7 times the quantity of 40 plus 22 all over 2, and we end up getting 217. Find the sum of the given integers from 1 through 35. So number of terms, 35, value of the first term, 1, value of the 35th term, 35. So substitute that into our formula. The sum of the first 35 terms is equal to 35 times 1 plus 35 all over 2, and we end up getting 630. B, 1 to 57. So we have 57 terms here. Value of the first term is 1. Value of the 57th term is 57. So we substituted in the sum of the first 57 terms is 57 times 1 plus 57 all over 2, which is 1,653. Find the partial sum of an arithmetic sequence. Find the 50th partial sum. So we have the first 1, 2, 3, 4 terms here. And I want to find the sum of the first 50 terms. That's the 50th partial sum. So looking at our formula, we need to know what the value of the 50th term is. So I know n is 50. I know the value of the first term is -6, but I don't know the value of the 50th term. So I have to do a little bit of work here first. So to find the value of the 50th term, we go back to like any problem on the first page using our arithmetic sequence formula. And since I know the first term, I'm using the shortcut formula here, but again, it doesn't matter. So I have C is a sub 1 minus D, so -6 take away 4. How did I find that D was 4? I looked at our example here. -6 plus 4 was -2. -2 plus 2 is 4. -2 plus 4 is 2. 2 plus 4 is 6, etc. So we get the value of our equation. The explicit formula for this arithmetic sequence is a sub n equals 4n minus 10. So now I can substitute in 50 to find the value of the 50th term to be 190. So now I have enough information to find the partial sum. So I substitute those values into the formula, and we end up getting 4,600. Do an application problem. Determine the seating capacity of an auditorium with 30 rows of seats if there are 20 seats in the first row, 22 seats in the second row, 24 seats in the third row, and so on. So we have 30 rows. First row is 20, then 22, then 24. So this is an arithmetic sequence with a total of 30 elements. So it appears that our common difference is 2. We're adding 2 each row. So n is 30. The value of the first term is 20. I need to figure out how many seats are in that 30th row. So again, very similar to the last example, I have to first find how many seats are in the 30th row before I can find the sum. So coming up with the explicit formula, again, using that shortcut since we know the value of the first term, we get a sub n equals 2n plus 18. That's our explicit formula for the sequence. So now I can substitute in 30 to find how many seats are in that 30th row. Now I have enough information to find the sum of the first 30 rows. So we have 30, that's n times the sum of 20 plus 78 all over 2. And we end up getting 1,470 seats. I'm going to end our lesson with a quick little history note about the mathematician Carl Friedrich Gauss and how he came up with the partial sum of an arithmetic sequence. So Gauss was a German mathematician who contributed to many things, but as the story goes, when Gauss was a young boy, he was given the problem to add the integers from 1 to 100. Remember that there were no calculators in those days. As the other students struggled with his lengthy addition problem, Gauss saw a different way to attack the problem. He listed the first 50 terms and then listed the second 50 terms in reverse order beneath the first set. You can think of it as he wrapped the series back onto itself. So for example, Gauss then added the paired values, noticing that the sums were all the same value. Since he had 50 such pairs, he multiplied 101 times 50 and obtained the sum of the integers from 1 to 100 to be 5,050. Now Gauss's discovery works nicely as long as you have an even number of terms, but it doesn't necessarily have an even number of terms if it's wrapped. So the number of terms is odd. You do not split the series in half. Simply list the entire series forward, then list the entire series in reverse and add the pairs. In this situation, you will need to multiply the sum by the number of pairs and then divide by 2, since it's actually working with 2 complete series. So by observing the series from both directions simultaneously, Gauss was able to quickly solve the problem and establish a relationship that will still that we use today. So in general terms, what he did was he listed out all of the terms and then added the first and the last, multiplied by the number of terms there were, and then divided it by 2 because the sequence wasn't really listed twice. So there's our formula. So pretty amazing. And when I learned it in my grad school, it was a much more embellished story about how he was in like first grade or something, and the teacher wanted to give the kids busy work, so they said do this, and he handed in his answer within like a couple seconds and baffled his teachers and everything. So I don't know how much of that's true, but we do know that he is the one that did come up with this formula by, again, just looking at patterns. And really that's all mathematics is looking at patterns and coming up with a sure way or formula to get things done. So hope you enjoyed today's lesson. I have office hours on Friday. Sorry about that. Forgot what I was doing in the middle of my sentence. I have office hours on Friday from 10 to 10:30. So if you have any questions over today's lesson or today's homework, just let me know, and I will see you at office hours. Otherwise, stay safe, stay sane, and please stay distant. We're almost hopefully at the end of this. Bye.